Can you all hear me okay?
Yeah.
Great. Well, this is exciting. I have to ask, without any introduction, how many people have seen the 120-year version of Moore's Law? This is an abstraction. And I just want to get a quick count of hands, maybe 15, 20%. Okay. Now, that's less than the number of people who said they were here last year, and I show this slide every presentation I ever give. So someone was either not paying attention or left the room. And the reason I keep showing it now for over a decade is I think it's the most important thing that's ever been graphed, and I think it will motivate much of what I have to say that follows. And in fact, it motivates much of everything we invest in. Almost every investment thesis we've ever had in some way revolves around this abstraction of Moore's Law. By abstraction, if you notice the y-axis, I'm just looking at how many calculations per second, how much computation can you buy for a buck? Could have been storage. Those are the two things you usually buy. You don't buy transistor counts. What Gordon Moore actually observed in the belly of the semiconductor industry was a refraction of this much longer-term trend. Okay. Now, there are these different technology epochs in these gray bars. These are everything from mechanical devices that took the census in 1890, the vacuum tube-based computer that predicted Eisenhower's win in 56, or even back in World War II, the relay-based computer that cracked the Nazi Enigma code, if you watch The Imitation Game. Well, what's interesting is that if you plot all the computers, the best price performance computers of the day, over 120 years, they fall on a slightly upticking line on an exponential curve, a logarithmic curve. If you'll notice the axis on the left, these are 100x improvements with each tick mark. All right? No one knew they were on the curve until Gordon Moore gave it a name and called it, and George Gilder called it the microcosm and said it had something special to do with semiconductors. It didn't. Humanity's capacity to compute has been compounding continuously from the beginning of measured time. Why? It's almost a cosmological question having to do, I believe, with the recombination of ideas and really speaks to the technosphere and why it's so powerful, why it's so different from other parts of the economy. Notice it's exogenous to the economy. World War I, World War II, the Great Depression have had no impact in humanity's capacity to compute. It's compounding innovation in these domains. Pretty amazing if you stop to think about it. It also gives us great hope. What if this curve continues for just another 20 years? This is where Kurzweil and others conclude we'll have machines that exceed human intelligence. And within 30 years, machines that exceed the intelligence of all humans on Earth combined in a single machine. They cost about $1,000. So available to many people in the room. It also begs, what is the next substrate? Is it electronics? Is it quantum computing? Is it something that's not just CMOS silicon the way Intel would make you believe it? So the thing to realize, if you label these curves, is Intel, about 10 years ago, gave up the mantle. Let's see if I can go forward one. Let's just stop going forward for some reason. Oh, and then went back. And it caught up. Okay, labeled here. The last 10 years, it's been NVIDIA. No surprise to anyone in this community. If you're going to buy a compute engine, you don't really care about Intel CPUs much anymore, other than the UI and, of course, all the other Windows delights that you are still encumbered with. If you're actually doing research, you want to be on a substrate that more sort of closely mimics the human brain. It's massive connectivity, its local memory, its ability to do much more in a massively distributed way, because that's really what deep learning and neural networks are all about. For anyone that's having a hard time reading it, it's the GPUs you can buy for a couple $1,000s today that are really the workhorses of deep learning. Now, I'll come back to the computational substrate later. The main point I want to make now is that we rely on this when we invest in new startups. As the capacity to compute reaches thresholds, you can simulate something that wasn't simulatable before. A trial and error science becomes a real information science. And I believe every industry on the planet will eventually become an information business. Something where the basis of competition is how good is your software, how good is your algorithm. You've seen that, of course, with cell phones. You're starting to see that with cars. The best car of the future will be the best AI. You won't care about how many cylinders your engine has, because, of course, it'll be an electric car. That won't really be the point of differentiation. You can see the advanced form of what hardware becomes, software-defined hardware, in the phone in your pocket. That's what satellites, robots, cars, and almost every other physical product will become over time, which has all kinds of profound implications on a winner-take-all economy and network effects, but I'll leave that for another talk. I'll just give you some examples of companies that we're investing in that obviously leverage deep learning as the basis of competition with their competitors. And I think you might be able to make a similar comment as what you might have made 10 years ago, or let's say 20 years ago. If you don't have an internet strategy as a new tech startup, what are you thinking, right? And maybe 10 years ago, if you didn't have a mobility element to your tech startup strategy, you're a little out of touch. And I think today, the same can be said for deep learning and artificial intelligence in general. If there isn't some machine intelligence element to your business proposal for anything launching today, what are you missing, right? And so any entrepreneur, you might ask yourself that. Across many different sectors, this is just a random sample, by the way. We, by no means, have a representative portfolio of everything that's going on out there. In fintech and a bunch of areas, there's a lot of financial tech, that is, a lot of innovation to be applied. Okay, I'll just show some visuals of some of these. Robots. Take a robot use all the off-the-shelf components that you get from cell phones, the accelerometers, 6-axis accelerometers, and put them in every joint. You make a dirt cheap hardware device where all the software updates, of course, are what people buy. And the reason you buy one product over the next is based on the software, not the physical change. You know, again, keep thinking of your phone. The next phone you buy will look just like the phone you own, right? It's just going to be Moore's Law and better software and services. The cars, you've already heard some about this. These are a couple in our parking lot that I love. I've been in a lot of these vehicles, and there are times when you want to, sort of be a driving machine, as some companies might advertise, and there's times when you want to be driven by a machine. And believe me, it's an increasing percentage of my commute. The thing that's interesting about this, of course, is where it will go in the near future. There are many vehicles driving all around San Francisco and the world fully autonomously in urban environments. And the frequency at which they need to sort of bail out for a human teleoperator to make a judgment call is increasingly dropping. And I think it is realistic to think that these will be in service in a couple of years with an Uber-like service. And it's a compelling vision. No driver, no ability to have a driver. Just get in and you be taken to where you want to go with a higher safety, reliability, and, of course, luxury than you've ever had before. The thing that these companies all need to make their driving algorithms better are huge data sets, right? So there's an interesting thing in the whole autonomous driving community of who's gaining the data, who has the most miles with which to train these neural networks. And some might say the cars on the road with these features have a clear advantage, right? One of the techniques many of the new entrants are using, those who aren't yet on the roads, is to train entirely within a simulator, built in many cases off the Grand Theft Auto. And so I find it somewhat humorous. Oh, by the way, they're cross-correlating, of course, like what they really see and what all the sensors would have seen in this 3D rendered world. They feed that through the sensor, and that's an entirely physical simulation, and cross-train with the real world. So I think the good news is that if the zombie apocalypse comes, the vehicles know exactly what to do. They'll be up on the sidewalks, they'll be taking out everybody, and maybe like an Easter egg, if you will, in the algorithms. But we'll leave that for the rapid-fire session on AGI later. Okay, not too far from now, we're going to have all kinds of satellites skimming around the sky. Within a couple of years, you'll see the broadband networks providing broadband data connectivity everywhere on the planet, ubiquitously, with a $200 ground station. This is coming from a couple different companies that are in development. That's going to extend global internet connectivity from 2 to 6 billion people much more rapidly than anyone is forecasting. Just take that into account also when you think about new business propositions. The developing world is going to come online en masse. But the Skynet I want to talk about first is one that is actually shipping as we speak this year. And that is a huge array of hundreds of satellites that are observing every meter of the Earth every day. And I'll just use this as one of the examples of how one of our portfolio companies is using deep learning in a way that they have to and is becoming the basis of competition in industry in transition. And that's an Earth observation, right? Taking pictures of the Earth, whether it's visual spectrum, infrared, synthetic aperture radar. There's all these different modalities, but you're just basically looking at Earth with a telescope. This is an example just of how the industry changes. Instead of these huge, expensive, mainframe-sized and mainframe-priced computers you're using, again, cell phone components off the shelf. Every part is a commercial off-the-shelf part in these sort of flock of doves, as they call them, satellites that observe the Earth. This is a company called Planet Labs in San Francisco. What they can do, though, let me go back just to see this visual. Imagine you have hundreds of these satellites blanketing the Earth, imaging every meter of the Earth every day. Right? You immediately start thinking, I have to switch from human analysts, like eyes on Kuwait, eyes on Afghanistan, to a blanket algorithm that's looking at everything for change detection, for, did something just happen? And then you automatically task a higher resolution satellite to zoom in on anything that's changed. Change could be environmental. Change could be natural disasters. Could be conflict zones. It could be new construction, new housing starts globally measured every day. It could be where are people parking? Count every car in every parking lot every day. No human would do that. It becomes a computer vision task. Some of the recent stuff they've done just in the last couple of months is to automatically detect any new wells that are being built or any oil and gas development going on anywhere in the world, whether it's in the U.S., Siberia, or you pick it. And you have all these sliders. What's new? What's changed? What are people doing? Or who's got swimming pools? A bunch of people for insurance adjustment, they just want to understand where are the swimming pools, which of our insured properties have them, which don't. Simple stuff like that. Or in terms of natural disasters, you can look at reflectivity of the water and actually the depth of the water using synthetic aperture radar to figure out what's been flooding, what's not, where are roads passable, where are they not for relief workers. You can also identify when there's new roads. There's a lot of places in the world that don't quite keep up to date on their maps, especially places like India, Syria, just discovering where's a new road popped up and be able to use the diff between before and after with daily imaging. Now, let me just end that section to say, there are many areas like this where the point of differentiation shifted from, do I have the best resolution? Do I have, I don't know what, some other parameter of metric to who's got the most data. And all these algorithms really only kick in on massive data sets, and that's what we're now getting. More data streaming down from these satellites than you could ever imagine. And you start to want to put the deep learning networks and the inference engines into the satellites themselves. Because what you can do is avoid sending down all the data that's exactly like what you had before. So let's say you're going over the open ocean. Unless you're trying to measure ocean levels, just send data sets if there's a ship in the photo, right? So 2/3 of the Earth are going to be over water. Don't even send down the images unless something's there worth seeing. And that kind of intelligence in the little devices that are everywhere is important. I'll come back to that later, that I think you're going to see an enormous explosion of intelligence on the edge, out in the satellite, not just in the data center, out in the remote sensors, in the light bulbs in your home, and every appliance in your home will have a little neural net in it soon. And let's say in the next 3 or 4 years, that will allow you to speak to it, will allow it to be much more intelligent than any of the Nest or drop cams are today. Is that really someone you should be taking a picture of, or is it just someone in your household? All that intelligence moves to the edge, I think, because the computational substrate is going to allow it to. So let me switch to that. Last year, for those of you that were here, I showed this slide of a general, and I won't belabor it today, of the migration that's been going on in Bitcoin mining. Actually, I could have said, this is what's going on in Bitcoin mining, of course. We're on the far right side of the page. And it's happening in deep learning as well, right, where we're somewhere between the GPU, FPGA, and ASIC side, right? Microsoft, in the last years, finally really embraced the FPGA research they've been doing for years. For like 4 years now, they've been trying to incorporate FPGAs, these are these field programmable gate arrays, into their servers. They're now putting one of those in every server they put in the cloud for their cloud services. And then the ASIC companies, since last year, both Nirvana, which we invested in, and Movidius, which we invested in, were acquired by Intel in the same month for the same amount of money, which is really weird. It's like a chip of $400 million. Boom, here you go. Both companies, same amount. And that's being incorporated into Intel's product line, and we'll see a lot coming out of that. I also mentioned Mythic. Let me just tell you, just as a reminder, what they are. That's sort of, you start to break the ASIC category into digital chips, and now I think maybe increasingly analog and quantum chips, or quantum processors. You see some interesting work. I'll just summarize for anyone who didn't see Mythic last year. They're building an analog deep learning harness, and for a sense of the power of this, and how it's, again, one step closer to the biomimicry of the brain, they're putting all of the computation in the memory array itself. So the memory is the computer. And for a sense of how radically different this is from any other chip in development, they can do matrix multiply and add, which is the thing you want to do over and over again, right? They can do 8-bit matrix multiply and addition in a single transistor. So usually that makes people, 8-bit multiply and addition with one transistor in that array, and it's in a standard flash memory array. That's one of the kinds of architectures I think that lets you put a 40-cent chip into anything, right? Into your iRobot Roomba or your microwave oven or your video camera. It's cheaper than the plastic buttons you might otherwise have to put in a device to give you control over its functions. You can just speak to it in natural language. So the kind of power you see with an Alexa home product that needs internet connection and needs a lot of power would fit into, a watch. It could be doing translation on the fly within a hearing aid. Just get a sense of very low power. But I want to spend most of the rest of my talk on building on something you just heard about, how quantum computers might affect this. As you know, CDL added an entire quantum machine learning track to their usual machine learning sort of accelerator program they're going through. And that was really exciting. Yesterday, a bunch of companies were presenting on how they're using quantum machine learning to do things like better chip design, quantum chemistry, and so forth. The thing on the far right, you've heard a bit about just in the last talk, that there's a lot of potential to do more than we have done in unsupervised learning, in generative types of architectures. And the reason, in a way, they've been held back is because of the compute architecture. Just like Hinton and team had a major breakthrough in 2012 in deep learning, powered largely by the GPU realization that, oh my gosh, CUDA and NVIDIA allows us to do so much more than we could before, and they really knocked the socks off competing algorithms in computer vision. Similarly, I think quantum computers could allow you to knock the socks off on unsupervised learning and generative design. I'll show you a couple examples. So, oh boy, I didn't realize this was build. Okay, so there's an interesting quote, and this will be with some people you know. Unsupervised learning had a great catalytic effect. Most of the research you've been hearing about today is in supervised learning. But these folks, who I'm not always reveal who they are, why keep it a suspense? Folks you know well, right, from the local community, really believe, in general, there's a lot of opportunity still to be done in unsupervised learning. This is largely the way babies learn, right? You don't say cat, 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 cat. They just They just bootstrap from the start. And whether it's the incredible work we'll hear more about later with AlphaGo Zero or others, when you have some of these minimal, well, that's not entirely a good comparison, but when you start from scratch, you can do so much more. Now, some of you may know this, but I think this is the first and maybe only Canadian company to be on the cover of Time magazine. D-Wave, on the other coast, so well, you know a lot about D-Wave. So what I love about this article that came out, a while ago, a couple of years ago, is that they quote one of the patron saints of quantum computing, David Deutsch. It was his book that first inspired me to invest in D-Wave back in 2012, and I've been on the board there for 15 years. But it really does provoke your thinking to perhaps ask the question, is this unlike anything you've seen before? Is this now something completely different, something frame-breaking, perhaps that framework of Moore's Law that we saw earlier? So let me tell you a few examples about this. There's this fellow on the right, Jordy Rose. He's here in the audience somewhere. He was judging. Oh, here he is. Huh. Yeah, the big black box. Yeah, he's a wonderful fellow. He's at a new company called Kindred. But his first company was this one. We met back in 2002. He had 1 qubit. And he was very excited that his second qubit was in fabrication, but not come out yet, not been characterized. It's hard to have entanglement with just 1 qubit. So, but he was convinced that the number of qubits would double every year, right? So he had 1 data point. The second one was coming. They're about a year apart. It's kind of like, Gordon Moore had 5 data points in his original article, and he just sort of plotted the line forever. Well, Jordy made that virtual plot in his mind. So I pulled this slide together, actually, in 2012, based on the blue dots, and I was kind of impressed. 10 years later, it held true. And then we've added the yellow since I first called it Rose's Law, because he's too, I guess, humble to call it in his own law. I've added the yellow dots as well. And so there is a separate question, which is a really hot discussion in the research community, which is, does the power of these systems scale linearly with number of qubits? That would be the worst case. 2 to the nth power, which would be the case in a sort of pure gate model quantum computer, that as you add qubits, the number of representational memory states you can represent with your computer grows as 2 to the nth power. If it were that, it would leave Moore's Law behind. Once you've crossed it, there'd be no looking back. There'd be no way for a classical computer to ever compete with a quantum computer once the quantum computer sort of crosses over. And those lines are arguably either already crossing over, or depending on the application, or about to, depending, again, on the software layer, which is where all the excitement is right now. Now, Google's been using these things for a decade, and they've been publishing results for quite some time. I find this quote to be really fetching and provocative in so many ways. I mean, of course, there's the unknown laws of physics. It begs that question. But as long as we just go with what we know, they think there's no better way to do creative problem solving. Now, this is stuff that they published in 2009. And they've been continuing to publish results saying, oh, by the way, the D-Wave machines that we use currently outperform our data center in machine learning, classical machine learning, as well as some new stuff in Boltzmann sampling. And weirdly, none of Google's competitors have bought a machine yet. So I don't quite know why they are alone in this, but they bought one of every machine D-Wave's ever made, and they put a forward contract to buy one of every machine they will make, and they're making their own internally as well. So they're all in, and they're getting some great results. In fact, one of their papers, just a couple of years ago, found that in a particular, how should I put this, almost like benchmark test that they purposely made to show the maximum differential advantage possible, so it's a trumped-up example of sorts, but they found 100 million-fold speed up over their data center. That's the kind of thing that you say is frame-breaking, right? Those are the kinds of order of magnitude improvement that catch people's eyes, usually. And it did, at least in the U.S. It's kind of interesting to me that every customer of D-Waves is in the United States and Europe. Let me just mention that to all the Canadians in the room. I don't know what the hell's going on, but everyone outside of Canada loves them. And they show some amazing work. Here's one on quantum Boltzmann sampling related to what you just heard in the prior talk, where you have classical algorithms in blue and green that in some cases don't even converge to the right answer, and they certainly don't do so as quickly as a quantum learning machine, where you want to sample from a probability distribution, and you want to do so in the minimalist number of samples. This recently has been shown, for example, in a completely different piece of work, to be a way to dramatically improve ray tracing in computer graphics. Like if you have Toy Story or some movie based on three-dimensional objects and you want to light and shade the scene, they've realized that by dropping basically a Boltzmann sampling engine, not a quantum one in that case, you can dramatically improve the results of even mainstream applications like ray tracing. So if you could get a further improvement still, and thanks, Barney, for that example last night at dinner. The credit to that summary goes to him. This could be a big, widely applicable area. I think Boltzmann machines in general haven't been used nearly as much as they could simply because they're so computationally inelegant on a normal single processor. Now, I want to go, let me come back to this just one sec. So the point of this was, in native sampling and in a bunch of areas, a quantum computer might get to an answer with a sparser data set or more quickly, or both, and more accurately. So this is really exciting in a lot of areas where reducing the amount of training needed to bootstrap the algorithm is pretty exciting. And so here are some results from yesterday. They were just came out. And the application was to go back at the data set that CERN gathered looking for the Higgs boson. So, we have all this data. Would a quantum computer have found the results more quickly? And amazingly, they found that going on a much smaller data set, if you looked at, oh, by the way, on this graph, notice that it's a 10 to the third power. So between the 0.1 and the 1, this is like a 1,000-fold improvement. The curve that gets up more quickly up on the lower error rates is the one that's using quantum sampling. So you can take, arguably, a dramatically lower sample set to get to the same results or better. Oh, I accidentally covered up there's a little formatting error there. Sorry about that. Okay, let me just end with something that's really interesting to me as a generalization of the power of all of these systems. So if you look at everything in the blue boxes, and some of these are very, of course, familiar to everyone in the room, biological evolution, traditional, plain old evolution, as well as artificial evolutionary systems, directed evolution that's sometimes used in microbial design. If you look at cellular automata that Stephen Wolfram wrote about, and there's a little picture in the top right there to remind you, cellular automata is a very simple piece of math applied iteratively over and over and over again to generate, in some cases, very complex and non-repeating patterns. Genetic programming, a field that kind of came and went. I'm not sure if it'll come back, but it literally involved mating and selection pressures on pieces of code that would cross-swap with each other, and you'd sense program a solution. It, in my opinion, had the most application in that things like that little antenna that looks like a bent-up paperclip. It actually flew on an NASA satellite. It was the most efficient antenna at a particular task, in a particular passband, a particular frequency. No engineer can understand why it's a good antenna. They can't learn from it. All I know is that using a generative process, they can generate antennas over and over again that exceed human design. They can also do it in analog chip design, where you have a number of resistors, capacitors, inductors. What combination of these, let's say, might make a bandpass filter or whatever you're trying to design, and they've actually generated patented results that exceed human design capacity. And the thing that method uses, just to explain why I belabor this, is you have a very easy testing mode. Is this circuit, like in a simulator, you can simulate, does this circuit do what I want it to do or not? How good is it at that? Great. You can test all day long. The generation part, what is the circuit that would give me the features I want? No one knows. So you either use human design, in some cases you can pencil it out, or you use these generative methods and basically test millions and billions of variations and slight permutations. You get to a design space that's unlike anything a human has designed before. And the last one, generative design, is the little animated GIF that you're seeing there. Autodesk and others have realized that if you apply some of these methods more broadly to manufacturing in general, you can come up with stronger things like a motorcycle truss in this case, or an entire dune buggy, or a bridge, than anything a human has designed. But you look at them, it's striking in a number of ways. A, they're almost all organic looking, as if it grew out of some garden. B, they're a little hard to manufacture in many cases with modern methods. You think, in many cases, you have to go to a 3D printer to make these things. But you could constrain the generative space, and they have to say, well, what if I only had straight beams and connectors, and you can get these sort of Tinkerbox-like things that do this job as well. Again, better than human design. Now, the reason I'm listing all these is that I think all iterative algorithms, deep learning neural networks is an iterative algorithm, right? Matrix multiply, back propagation, gradient descent. All these things are do some simple math over and over and over again. And in the complexity of billions of these things, eventually trillions of these things, you get the emergent beauty of what we are all here today to celebrate. But I think there's something to realize that what they all have in common. The artifact of creation is inscrutable as to its inner workings. So I think when we, for example, use deep learning to grow an artificial general intelligence, an AGI, which we'll talk about more in the afternoon, that's perhaps comparable in complexity to the human brain, it'll be easier to build a new one than to reverse engineer its own workings. I think we'll build an artificial general intelligence that exceeds human intelligence before we ever understand the human brain itself. Reverse engineering our own brain is more difficult than building a new one. And you see that in small cases today throughout the industry. The practitioners in this field have a tough time sometimes integrating with the rest of the development environment, where engineers and engineering managers say, well, how do you know it works? Tell me how it works. And they're like, I don't know how it works. I can tell you how I made it. I can tell you how I make a better one next time. the locus of learning switches from artifacts of creation to the process of creation. And it's so different from normal engineering modalities. It's not like the Germanic approach of it does what I say, and any variation from what I say is a bug, right? This new design modality is more like parenting, right? You don't go in and tweak the neurons of your teenager. The best you can hope to do is a better job parenting next time around, if you know. And that's this long game. That takes years and decades, but we get slightly better. Cultural evolution and what have you, we get better over the eons in this task. But you don't go in and ever imagine you're going to tweak the artifact. And I sometimes see people conflating those. They imagine that they're going to grow an intelligence through something that feels like deep learning, and then when they're done, they can do cut and paste on the subcomponents. No. It'll be like an alien intelligence defined by its interfaces. And all of the beauty within is as inscrutable as the brain. So I think for a lot of reasons, that metaphor is important. And I'll leave it at that.